And now it's my pleasure to introduce this morning's keynote speaker, Alexander Rose. Xander is Executive Director of the Long Now Foundation, which was an organization founded in 1996 to foster long-term thinking and responsibility. This keeps forwarding on me. Apologies for that. As director, Xander's been responsible for several activities at the Long Now Foundation, including founding The Interval, which is kind of a bar, cafe, museum, conversation space for future thinking ideas. He also has led a range of projects. They really want you to speak. One of which is the Rosetta Project, a collaboration of language specialists and native speakers who are building a publicly accessible digital library of human languages. And another one of which is called The Long Bets, which is a public arena for competitive predictions on questions and issues of interest to society at large. He shares with computer scientist Danny Hillis several design patents on the 10,000-year-old clock, the first prototype of which is in the Science Museum in London, and the monument scale version that's now under construction in West Texas. Xander graduated with a Bachelor of Arts degree in Industrial Design from Carnegie Mellon University. He attended the Art Center College of Design in Pasadena, California. Sorry, Xander. He was an artist in residence at Silicon Graphics and a founding partner of the robotics company Inertia Labs. He's built robotic bartenders, large pyrotechnic displays for the Burning Man Festival, and other dangerous machines. Xander will be speaking today about the building of the 10,000-year clock and how it can engage communities to think about the long future to help us be, as it were, better ancestors. So please join me in welcoming Xander Rose.
Thank you very much. Let me switch. Sweet. This project of the Long Now Foundation really began with a story, and it was a story that was told by Gregory Bateson to one of our founders, Stuart Brand. And it was a story about the beams here at New College, Oxford. And New College was built in the 1200s in Oxford, England, and about 500 years later, in the 1800s, these big, huge beams that went over the main dining hall, these oak beams, had become rotted and infested with beetles, and they didn't quite know what to do because you couldn't buy trees like this in Europe anymore. And it wasn't until they spoke to the school forester who said, oh, well, we have the trees that you planted. And it turned out that when they built buildings like this, they also planted groves of trees to maintain these types of buildings over time. And we now have other examples, for instance, of the Royal Navy in Norway that planted masts 200 years in advance of the needs there. And once when I was at the Vatican, I saw that all of the tiles that they used for the mosaics, they forced all those artists to do overruns 500 years ago of all of those to kind of maintain these. And this kind of thinking about centuries in advance, where you do something very small and simple, such as scattering acorns in the ground, to solve an intractable problem in the future, was something that several people that kind of heard this story realized was not the kind of thinking that we were doing now. And Stuart Brand went ahead and told this story to computer scientist Danny Hillis, who had been building the fastest supercomputers in the world out of MIT with his company Thinking Machines, the computers that are now often what we now base most supercomputers on, such as cluster computers with massive parallel processing. And he had been kind of tasked with building these fastest machines in the world his whole life. But he realized that there's problems such as climate change or hunger or education that could only be solved on multi-decade long cycles. And so if we aren't going to work on problems of this time scale, then those problems actually just came off of the table. And he realized that we needed a kind of a corrective to this. And his thought was to build not the fastest computer in the world, but the slowest computer in the world, as a kind of icon to long-term thinking, and something at kind of monument scale that would get people's attention. And Stuart Brand, who had started the Whole Earth catalog back in the 60s and been kind of hacking culture his whole life, realized that if you get people's attention on long-term thinking, what do you do with that attention? And his thought was a library or an information storage service that would last also over these kind of millennial timescales. And then this whole group of people that were mostly technologists from the first generation of Silicon Valley and more recently some of the next generation of Silicon Valley, all, I think, in the 90s were feeling this increased pace of culture, and that pace of culture was at a detriment to solving some of the world's largest issues. And this started as a discussion, and then one of the first questions really became, what kind of time scale, if you're going to do something that gets people's attention over a long time, what time scale should we use? If you start to look at something like these galactic or astronomic time scales of billions of years, it's very dwarfing to the human experience, or the geologic time scale of millions of years, it still is very difficult to feel how you might have an effect over this time scale. But if you start to look at really the length of time that humans have had cities and civilization, modern civilization, around 10,000 years, this becomes a more tractable amount of time. It stretches us from where we are now, but we know that we have artifacts that span this kind of time scale. But I think the most important thing to look at in a diagram like this is that we're not just talking about the last 10,000 years, we're talking about the last and the next 10,000 years. And that thinking about ourselves in the middle of a 20,000-year story, rather than at the end of a 10,000-year story, which is, I think, what we the narrative now is that we are at this end of a story. And I think, humans are a tenacious species. There's very little that's actually an existential threat to us. But we aren't really acting as though we have the right half of this graph in front of us. And one of the first things that I worked on this project with Stuart Brand and Brian Eno actually was this diagram of trying to tease apart the layers of human time. And the fastest and most frenetic layers on the outside, fashion, and I would even put some of the web and communications technology out there now, commerce, and then infrastructure and governance and culture, and then the slowest layer being nature. And you can imagine how you could place all kinds of things, and especially a lot of the artifacts here at the Smithsonian, or the artifacts that you're digitizing that cross over many of these. But one of the things that this diagram was very helpful with was kind of teasing apart projects and activities that maybe if they skip some of these layers, that you can see how they might be a problem for long-term thinking. So for instance, when Maxam Corporation bought Pacific Lumber in the Pacific Northwest, and Maxam's general MO was to sell companies for all of their assets because their assets were worth more than the company it was itself. That company's assets happened to be old-growth redwoods, right? So they were working up in here in this commercial layer. They were making a very smart business decision, but they were taking out trees that were over 1,000 years old, and that ecosystem that would basically never be replaced. And they had skipped all of these other layers. And then all of a sudden, culture and government jumped in and stopped this effort from happening, and so now it's kind of a lot of those trees did get cut down, but a lot of them also got saved. But it was an example where by skipping a bunch of layers, you kind of miss the part where you're serving civilization correctly over the long term. So I'm going to talk about some of my research into things that have lasted over the kind of timescale that we're talking about, and then I'm going to talk more directly about the project itself that I'm working on. And I think some of these objects are going to be very familiar to you, things like the Antikythera device. But this idea that one of the ways that something lasts is actually that it is both lost and it is found. For one reason or another, this device that was, let me get it, any movie? Oh, there we go. This device that was found at the bottom of the Mediterranean it was only conserved because it was lost. Clearly there was many more objects like this that were made, but only one of them has survived for over 2,000 years from antiquity. We don't really know why, but what we do know after doing X-rays and MRIs of these things, that we have found that what it was actually a kind of an astronomical clock of sorts. And now that we've recreated them, people have even made versions of these in Legos, and we have this amazing history of not only that sets back a lot of technologies of gear and astronomical understanding, but also this idea that if something is mechanical and understandable and lost, that even if we have fragments of it, we can put it back together. So for instance, if we were to build a clock that was electronic and we found it at the bottom of the ocean after 2,000 years, you can imagine how difficult it would be to understand its meaning compared to something that is mechanical, where even just fragments of it allow us to reconstruct it. When I started working on this clock project, the first material scientist that I talked to when we were talking about what materials we were going to make something that was going to last for thousands of years out of, and he said, well, basically you just have to realize that everything is burning just at different rates. And what he means is that oxidization is the kind of death of all materials, and that can be, that's rust in the case of metals, but it's kind of everything is oxidizing and going away. And one of the kind of most amazing examples of antiquity that I found that showed that people understood this from a very long time ago is this lacquer set. It was found in a tomb that's over 2,000 years old in Mongolia, but what was amazing about this tomb was that it was lined with cedar planks and then 6 feet of activated charcoal and then cedar planks and then mud, and they understood that activated charcoal was actually an oxygen getter that was removing oxygen from the room over 2,000 years ago, which I think is a pretty stunning piece of chemistry to have understood. And it's one of the only examples I know of that did that, and I would love to hear more if there's some here in the room. But they understood that everything was burning and that they just needed to figure out how to stop that oxygen from getting there. Now, of course, you all know as people who work in museums that if you're letting humans into the room, removing oxygen from the room is probably not something that you can do. So you have to work in materials that can last over that time with oxygen in the room. Another strategy that things have used or that has been used for objects to last for a very long time is this idea of a kind of an ablative layer, or a sacrificial layer. We see it in nature with something like a lizard's tail that comes off, and if, let's say, a bird is attacking the lizard and then the lizard goes on to live and it regrows the tail. But you also see it kind of these accidents of antiquity, places like the Taj Mahal that were crusted with all these jewels, and that instead of this building being razed to the ground, people spent a lot of time prying all the jewels out of the walls of this building, and they felt as though they had extracted the value from the building. But as we know, the architecture itself is one of the greatest gifts of this building. And even the pyramids and a lot of the sites in Egypt have this quality where all the expensive things were taken out of them. In case of the pyramids, even the outer casing stones were taken. But the value in the cultural parts of these and the architecture are still things that have remained. And that I think that by having some of these high value elements that are removable, you actually can keep possibly the higher cultural value objects in the end. By making something extremely remote, it's another strategy that seems to work. This is the seed vault in Svalbard. It was designed to last for 1,000 years. I was there a few winters ago. This is the runway as you land in Svalbard. It's the northernmost permanently inhabited place on the planet. But what was really amazing to me is you kind of go through these doors that store these seeds for the future is this sign-in book, and I was signing my name right after Ban Ki-moon and Jimmy Carter and this amazing set of people that had flown to this far, far remote corner of the earth to look at just a bunch of shelves, literally. But there's something about the remoteness that not only is a preservation technique, but it's also it creates a much more mythic sense of the thing that you're doing, and they didn't quite know what to do with how many visitors that they were having. Another way that you can get things to last for a long time is to just build them very slow. And one of the most difficult times for something to be preserved is often about 1 or 2 generations after it's created. It's not yet old enough and an antique, but it's in this kind of no man's land where it's just the thing that your parents' generation did and it's not cool. So if you have something like these cathedrals that took over 800 years to build. This is the cathedral at Cologne, Germany. It was took over 600 years to build. They kind of span that time while they're still being built through the time where they're trying to cross over that. And we see this in examples like the Sagrada Familia, which is 125 years into its build process. It probably has at least probably 50 more years to go, as near as I can tell. But it's already a UNESCO World Heritage Site, which is amazing because it's still under construction. It's the idea that a construction site is a UNESCO World Heritage Site, I think is an amazing concept. But it went through that very odd period about 50 years in where no one was working on it for a while. And in places like Japan, we see some of the best examples of maintenance in the world. These are two of the oldest continuously standing wooden structures in the world. They've been just meticulously maintained, and you go through them, and all the central beams are all still the same. They're 1,400 years old. And as long as you're maintaining things, as you know, as conservators, they can last. I mean, I was just upstairs. There's wooden statues from Japan over 1,000 years old. So the materials don't have to be these exotic, amazing materials, but if they're well maintained, they're kept out of the rain, the roof is kept on, they tend to work. And the other strategy, which I think is an interesting one, especially as you look at it from a digital point of view, is another site not far from the one that I just showed you. This is the temples at Ise, which are rebuilt in an exact replica of each other every 20 years. And so the one on the bottom is the new one. I was there in 2013 when they rebuilt these, the last one, and the Princess of Japan comes and she moves the treasures from one to the other to bring the spirits from one temple to the other. And then they deconstruct the old temple, and the wood and the thatch and all that goes out to all the other temples in Japan as kind of these prized items. But this is an amazing example where you have highly ephemeral materials being passed on in this kind of baton fashion of one generation to the next. Once every 20 years, you have a master builder teaching the next generation builder how to build this temple. And I think the physical act of doing that is also helpful for the Shinto belief system as much as it is for these objects. But if you can imagine, fundamentally, it's going to be very difficult for digital objects to last for thousands of years. These buildings are at least, this tradition has been going on for at least 1,600 years. The site's been operating for over 2,000 years in this fashion. But if you're going to keep something like a digital object going for 2,000 years, it's going to have a kind of a pattern like this, where it's handed from one generation to the next, from one technology to the next. Things that are underground seem to last for a very long time. It seems to be our strategy now for holding things like nuclear waste. This is the Onkalo nuclear waste site in Norway, which is designed with a 100,000-year design life. And here in the United States, we have a 10,000-year law on the books, actually, which is around storing nuclear waste, and places like Yucca Mountain. The other interesting thing is that the problem with going underground is that you often find yourself in a situation where you have to deal with water. All the underground sites that I have visited in my life all have a problem with water and how to deal with it, and they all start by thinking they can keep water out, and they all are wrong. This is the last picture they let me take as we were going underground at the Mormon genealogical archive bunker outside of Salt Lake City. But I did find some pictures online, and it's just a microfiche archive, but this is also a 1,000-year design life facility, and they don't keep any film in the bottom 4 drawer levels there because it's already flooded 4 or 5 times since the 1960s when it was built. Their biggest fear originally was nuclear Armageddon, but it turns out water has been a much bigger threat to their archive than anything else. And then even this pump system was added to that place in Svalbard because it was already started to fill up from water from unseasonably warm weathers where the tundra is already starting to melt into this facility. And the last one I'll mention is the most difficult one, obviously, if you're trying to get something to last for a very long time, and that is, the wrong ideology can make you a target of all kinds of horrible acts. And this is a before and after picture of the Buddhas at Bamiyan in Afghanistan, where the Taliban spent weeks dynamiting one of these statues out of the wall. And we've seen many more acts like this since, where the wrong ideology can just put you on the wrong side of modern activities. And there's really, I don't think, any great answer to this question so much as how do you create not only the artifact itself, but how do you create an institution that can keep it relevant and interpret it and protect it over time. So that's some of the research into how things have lasted either by accident or on purpose, and some strategies that we can use. I started working on building this clock originally as a prototype back in 1999, and we started with a set of design principles to kind of measure all other timekeepers against and see what parts of it we were going to use, and many of them are pretty self-explanatory. It has to last a long time. You have to be able to maintain it. Our assumption is not that it just goes on into the future without any maintenance. It has to be transparent. You have to be able to look at it and understand how it works. It should evolve. Things like, if we're going to have timing systems and calendar systems on a clock like this, we know that none of these have lasted over these kind of time scales. And then scalable. We should be able to make a small prototype and then scale up. And the first prototype, as was mentioned, was about 8 feet tall, and it's at the Science Museum in London. We have several others at our space in San Francisco. But now we're working at the full monument scale in West Texas, which I'll be showing you in a bit. But I wanted to show you kind of one of the types of design problems that we ran into when designing the 10,000-year clock. And this is a picture of the sun at noon through the course of the year. It creates a shape called the analemma. You've probably seen it out in the middle of the Pacific Ocean on some of your globes. But what it's showing you is something that's called the equation of time, which is really this kind of plus or minus 15-minute difference of solar time to absolute time, or clock time. And so our clock has a pendulum in it, and it keeps clock time. But it also has this part up at the top of the mountain that focuses sunlight in and expands a tank of air, and a mechanical bellows moves, and we get this synchronization event to solar noon. So we needed to be able to synchronize solar noon to absolute noon. And so there are clocks that have done this in the past, and they use a 2-dimensional cam that goes around once per year and gives you this plus or minus 15-minute difference. But the problem if you're trying to make a 10,000-year clock is that the Earth is also precessing on its pole every 26,000 years, and it's also slowing its rotational rate right now by about a second a century. And all of those things have to go into the cam that we built to adjust for the equation of time. And it's this 3-dimensional cam that goes around once per year, but the cam follower goes up it once over the course of 10,000 years. We left 1,000 years at the beginning and end so that you can make a new one before that time runs out. The full-scale clock that we're now working on, I kind of went through some of our archives and I realized it actually started with a scanning project. We have a site in West Texas. The project is funded by Jeff Bezos of Amazon, and he had this property there that had these amazing cliffs. It's not far from some of the large cave sites in New Mexico, natural cave sites, and so we knew that we had some good limestone to work with that has made underground spaces that have lasted for millions of years. But we wanted to figure out how to design the experience that people were going to have through the site and where the trails were going to go, and it started with a LiDAR survey. And then we started trying to build things underground in ways that other people had not before. We started with the oldest technology, which is blasting. We worked with a wine cave builders out of Napa, California, who really understood how to build things kind of artistically underground. This was the blasting plan that they came up with for one of the rooms that we were making. Each one of these outward lines is a drill hole. Let's see if my video's going to go. There we go. And what was amazing to me about this process is kind of one of the, aside from hand carving, this is one of the oldest processes that you have, and you're drilling a hole into the outer wall and then packing it with explosives and then blasting it, and then you come and you pull that material out after that, and then you end up with the final shape. But what was amazing to me is that working with these guys who are, the person who was designing each hole and specifying the explosives that went into it was in his 70s, and he had spent his entire life doing this, where he got the shape of this room to within 6 inches of our net shape using explosives, which was not a medium that I thought you could get that accurate with at the beginning of this project. And then, as you might imagine, that we went back and forth with laser scanning of this. In fact, Ping Fu, who I think worked with your digitization department here at the Smithsonian, came out and did some of the very first scans of the underground space as we were starting to work on it. And the site, as I mentioned, is here in West Texas. This is looking north. Those ranges in the north there are in New Mexico. We're right on the border there. You can see some of the equipment at the top of the mountain, and then the entrance is actually down in the shadow of this cirque that's right here. The idea is that you hike up from the bottom, you go into the mountain, into an opening that kind of looks like it might be a Mayan entrance or a natural cave opening, and then go through the entire clock experience, and then are reborn at the top and have this whole different appreciation for time. And so we wanted to build that experience almost like a Disney ride, in a way of how do you change someone's perception of time through this whole thing. And while we were able to start with some of these old techniques of moving rock underground, we had to move to new techniques that actually hadn't been designed before. We wanted to build this tapered underground vertical chamber where the clock was going to go, and we wanted to put in a spiral staircase, and it's all through solid rock, hundreds of feet tall underground. And this is not the kind of thing that you can do by blasting. You also overbreak the rock when you blast it, and so it becomes less stable for a surface that's going to be vertical like this or overhung like this. And we did see that in places like Carrara, Italy, they have kind of made these negative shapes using these giant diamond belt saws that are pretty amazing, but they're all just designed to cut blocks out and pull these blocks out and then cut them up into things like counters and floors and things like that. So what we did is we took one of these saws and built a 36,000-pound robot to drive it, and then started to cut layer by layer away, and then break those layers away, and we could get things like staircases and these tapered surfaces. This saw was pretty amazing. It could cut, this is accelerated a little bit, but it could cut through stone about the same speed as you might imagine a chainsaw cutting through wood. And this is the very first test that we did of it cutting stairs. Basically, it does all these horizontal cuts, and then you put some hydraulic bags in between the layers, and you can break those out. And when you're done, you end up with this pretty amazing stairs that were cut. The staircase itself was tapering through 250 vertical feet, so every single cut was different, which would have been really difficult to do by hand, as you can imagine. This is before we installed the railing. And some of the first parts of the stairs that were done. The machine itself, we're not done with this project. We don't have an end date for when we are going to be done with it, but I'm going to show you some of the very most recent installation work that we've done. We've built both the chime generator and the power system, and that's all installed so far. The power system for the clock, I mentioned, we do want visitors to come here. This is a visitor experience. And we not only wanted them to come, but we also wanted them to interact with the clock and to add power to it. So the clock gets its power to keep the time by the temperature difference from day to night with that same device that I mentioned up at the top of the mountain that synchronizes it. We pull some of the power, and so that keeps the pendulum going and keeps the clock ticking. But in order to show you the time, you have to wind it. And if all the parts, the dials and the chimes, all have to be powered by the people that come in and wind it. And the people are also kind of walking through this in an architectural scale. And so this is a fairly complex mechanical device. And one of our biggest questions really was, how do you keep not just the materials to last for a really long time, but something that has moving parts to last for this kind of time span. And when I started on this project over 20 years ago, we found exactly the right bearings to solve this problem of how do you have a rolling items that don't just freeze up over these kind of time spans. And it was ceramic bearings that were developed for satellites. And unfortunately, at that time, ceramic bearings cost about $50,000 each, and you couldn't get them in a lot of different sizes. But since then, they're now in rollerblades and fidget spinners and cost $5 each, and you can get them in every size. So the entire clock has these ceramic bearings where both the races and these outer rings and inner rings, as well as the balls themselves, are entirely made out of ceramics, which we know can last on these kind of timescales. And we have tested in terms of how many cycles. And it also means that we could do the entire clock with no lubrication. We're now installing some of the largest pieces of the clock. There we go. And this is the power system going in, working with an amazing set of fabricators. This is the winder in cast bronze with a stainless steel core. All of the engineers that are working on this project have been working on it now for at least, the shortest time is about 5 years, and some of them, along with me, for over 2 decades. A lot of them are this is their retirement project, where this is the last thing that they want to work on. But it's been an amazing group of people, not only working with Danny Hillis, but just working with kind of artisans and fabricators that realize that this is not just something that has to work, but something that has to be beautiful and engage people as much aesthetically as it is the way that it works. This is the drive weight getting installed. It's 15,000 pounds, mostly of concrete, but an outer bronze casing. As it falls, it creates, or it stores enough energy to run the clock for over a century, even without any auto winding or people winding going on. The other part of the clock that I mentioned is the chime generator. And so while this clock has kind of a lot of the same parts that a lot of clocks have, one of the parts that it has is a part that rings a series of 10 bells in a different sequence each day for 10,000 years. So a kind of mechanical computer that was worked out by Brian Eno and Danny Hillis, this algorithm that could ring these bells in over 3.5 million permutations over 10,000 years. So every person who arrives kind of gets their own version of what the clock sounds like. And then after we had built that first prototype, we had to scale that up and turn it vertically and make it in this kind of architectural scale that we just now finished doing this install. And this is probably the largest part of the clock and most complicated part of the clock. There's 10 bells and then 10 Geneva wheel mechanisms that run all those. And this was us installing it just a few months ago in June. This was the largest lift that we had to do. It was over 60,000 pounds, 80 feet tall. The main materials that we're using are 316 stainless steel for the clock itself, as well as titanium shafts, and as I mentioned, the ceramic bearings. When we install the clock, also there's no fasteners used to hold it to the walls. It's just these giant pins, and then it levers itself out and holds itself in entirely with friction. This was a very stressful moment right here, where we put the pins in for the first time, hoping that system worked really well. As was mentioned, the other side of this project is not only just getting people's attention around long-term thinking, but also, what do you do with that attention, and this information storage project. And we realize that if you're trying to store information on the scale of 10,000 years, you have a platform dependence problem, and that's language. So the very first problem that we wanted to solve on this time scale was language, and so we spent about a decade with an NSF grant collecting a really broad swath of linguistic materials, not a very deep dive, but a shallow but broad archive of as many languages as we could. And so We created a digital version of that archive. It's on the Internet Archive that you can access now. But we also created a kind of a microfiche that could last for thousands of years by microetching this language material onto a silicon disk using a gallium ion beam, the same kind of device that's used for prototype circuitry. But instead of circuits, we actually milled into that material the letters and pages that we had scanned. And then the disk had two sides. We've made several versions of the disk, actually, but one of them has two sides that kind of explains, on one side, at human eye readable level, spiraling down smaller and smaller, so you could follow it with a microscope and then realize what's there. The other side of the disk has 13,500 pages of language data on it. And we collected a number of things, like a parallel text and a basic description of the language and a map of where that language was found and an orthography and things like that. So that it would give you at least a reasonable jump start at understanding a language. And then most importantly, that it's this huge parallel data set that allows you to work from one language to the next, just like the original Rosetta Stone did that helped us with hieroglyphics, but hopefully with much broader than just 3 different scripts. One of these was actually launched on the European Space Agency's Rosetta mission that was launched in 2004 and then arrived at the Comet 67P in 2014, 2016. And that was on the orbiter that actually is now landed on the Comet and continues to orbit the sun as our kind of off-world language archive. And I'll just close with this story, which I think it's kind of resonated with me when I heard it. And fundamentally, there's a 1 in 10,000 year event that happens every day. Sometimes they're totally inconsequential things like a neutrino passing by or something like that. Sometimes they're very consequential events, such as an earthquake like this, like the one that created the tsunami in Japan in 2011. And that was considered the earthquake size was considered a once in 10,000 year event. But these tsunamis obviously have hit Japan from other earthquake events many times. And there was this story about these markers that were over 500 years old that people found throughout these areas in Japan. And this one read, high dwellings are the peace and harmony of our descendants. Remember the calamity of the great tsunamis. Do not build any homes below this point. And all the homes above that point were fine. All the things below that point were destroyed. And it's this notion of, that just because we're modern, that the past doesn't matter and it can't catch up with us is obviously a dangerous notion. And we're seeing it now with things like climate change and in this case, natural disasters. But being able to interpret the past can be as valuable to the present and the future as just about any other modern technology can. And I think it's always good to pay attention to that. Thank you very much.